Okay, so we're going to go over a quick video on big little logic. I'm going to try to keep this as short as possible. So just as a reminder, what we're talking about here, when we say limit, remember we're talking about y values, and when we say limit as x approaches infinity, don't forget, that's just talking about on this graph, whatever this graph may look like, we're talking about what is our graph doing as x goes towards really large numbers. So the big little logic is just kind of following that idea. What would happen to this function if instead of using x, if I filled in some number very large, squared it, and then added 3? So what we're saying here is like big, like a billion. And a billion wouldn't even be close to it. That's not a billion, that's a million. Let's give 3 more zeros. A billion! And that's still not even close to infinity, right? In comparison to infinity, that's nothing. So we have to keep that in mind. When we talk about big, we mean something gigantic. So a billion's a good thing to use in our brain, but no, that's still too little. So a billion squared plus 3. If someone told you I was going to give you $1 billion, then square it. So a billion groups of a billion times a billion, and then add $3. Yeah, you'd say, I don't care about the $3. It wouldn't be worth your time to take it from the person. You keep it. So therefore, essentially what we're looking at here is really this, because this number here might as well be 0. So now, what is the square root of something big squared? So notice now we're reverting back to a little bit of algebra logic. So you'd say, all right, the square root of something big is squared is just something big. And to our meaning here, when we say big, we mean infinity. So therefore, the solution to this limit would be infinity. And we can support that idea by looking at it on our graphing calculator, which I turned my resolution up so I could try something, and I can now no longer fit my calculator on the screen. So what I would suggest to you is type that in your calculator, and you will see what this graph ends up looking like is actually something like this. It ends up looking like that. So as your x values go towards infinity, you can see the y part of your graph is going towards positive infinity, like we saw right here from the limit. So there's the first problem. So for the next problem, our limit of this graph, what are we saying? Well, once again, it's as x approaches infinity. And to make our life a little easier, once again, instead of writing x, we'll write big, just to help remind us that what we're going to be substituting in here, we don't care what happens anywhere where x is 2 or 4 or 10, we don't care. What we're only focusing on is large numbers. So therefore, if someone told you you had $9 and then I'm going to take away e to the big, well, what is e to the big? Remember, e is approximately 2.718-ish. So when I say e to the big, what I'm saying is e times e times e times e times e times over and over and over, because the exponent is large. So if I did 2.7 times 2.7 times 2.7, that would be gigantic. So therefore, if you started with $9 and someone said they were going to take away $1 billion, or if you had $0 and someone said they were going to take away $1 billion, it might as well same place, doesn't really matter. So what we're going to do here is, by our big little logic, we're going to say these 9s don't matter. Now, sometimes students say, well, what about this 4? Can I get rid of that too? Well, no, you can't, because what someone here is saying to you is, in this denominator, would be like saying, you have $9 plus I'm going to give you e times e times e times e. That's great. But then someone says, not only am I going to give you that, I'm going to quadruple it. I'm going to take that amount of money, whatever e to the big is, and multiply it by 4. So I'm going to give you 4 times e 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 times e. That 4 is awesome. We're keeping that 4. So you can't just throw out the 4. So that's going to leave us with negative e to something very, very large over 4 times e to something very, very large. Now back to algebra logic. What we're essentially seeing here is e to the x divided by 4e to the x. So when you have two things that are the same, one in the numerator, one in the denominator, and they're all multiplying, we are now able to divide. So what we're going to go ahead and do here is we are going to divide. E to the big divided by e to the big leaves us with negative 1 over 4. So therefore, the limit is negative 1/4. And that usually leads to a bit of an issue when we get some other problems where you might have, I'm going to keep the problem very similar, 9 minus e to the x, except what I'm going to do here, what I'm going to do here is change the denominator just slightly. Whoops, I wanted to drag this down to give myself a tiny bit more space. There we go. Where I might have 9 plus e to the 2x. So does this 2 up here in the exponent matter? Well, it absolutely does. And does it affect my answer? Yes, it absolutely does. And here's the reason why. When we think about this is going to be e to the big over 9 plus e to the 2 times big. And for the same reason as before, we can throw out this 9 and the two 9s. It's not that they're dividing. They're most certainly not dividing. It's big little logic that's letting us do this. We're saying in comparison to the thing it's subtracting, it's insignificant. It might as well be a 0. So, just as a little brief reminder, if you have something raised to an exponent, so such as x squared raised to the 4th, that is equal to the same thing as x raised to the 2 times 4, or aka x to the 8th. So therefore, what we're seeing here, if we work backwards with that idea, I can say this is negative e to the big divided by e to the big squared. So therefore, you can see these bigs are not equal. This big squared is much larger than just a big. And if you think of it like normal exponents, how would you do something like this? Well, they would divide. You would say x to the 4th and the x to the 8th, exponents subtract. So that's what we'll do here. This would be e to the big would divide with e to the big squared, but leave me with just 1 e to the big in the denominator. So that'd be negative 1 over, yeah, that's right, over e to the big once again. So now negative 1 over e to the big is something very, very large. So the idea of I have one piece of bread, I'm going to divide it amongst everybody on Earth, that would result in something very, very small. Or I'm going to have one thing and divide it into infinitely many pieces. And you could argue it's negative small. That's fine. It's negative 0 and 0. Just describes which way on the axes your graph is approaching. And in this case, we're going to approach from the bottom side. But whatever the case, who cares? The answer, the limit is 0. Okay, so one more problem sometimes people like to run into is trig. So when we look at this problem, we're going to use very similar logic. So we're going to say this is e to the negative 3 big times cosine of something very, very large. So now, if we evaluate the negative exponent, it might help us out a little bit. Because what is a negative exponent? Well, it's just, you can be rewritten as the same number, just non-negative in the denominator. So now, what is cosine of something very, very large? Well, from what we should know about cosine is that's a function that just oscillates between negative 1 and 1 repeatedly. So therefore, our numerator is going to be either negative 1 or 0.5 or something, but it's going to be some value between negative 1 and 1. So whatever that value is, it's something small. It's something 1, 0, negative 1, whatever. Something in comparison to this, it's something small. So who cares? Throw a number up there. Now, in the denominator, e times 3 big, that's just going to be something very, very large. So therefore, 1 divided by something very, very large is something very, very small. And if you go ahead and graph this whole function, what you'll see is it's very interesting. It ends up being something that oscillates very large, and then right here it ends up getting to 0 very, very quickly. So it supports that our limit is 0. So I hope this helps with big little logic. Best of luck.